You started to say, oh, so we're going to talk about G. And I'm like, wait. We need to hit record. We are talking about G. And I think I know what. Oh, actually, okay, there's lots of G's that just flash before my eyes that I'm like, it could be this, it could be that. So
there are a lot of G's, right? Yeah. We are talking about the big one, the big G.
Capital G.
Capital G.
Okay.
Which is actually how some people refer to it, is capital G.
Yeah. Because there's another G that's in the physics news these days. And that's what I thought you were going to talk about. But no, it's the capital G.
Yeah.
This not one, the G factor.
Not the G factor, no.
Right.
This one is slightly in the news, a little bit. Not the news, I wouldn't say, but like, physics background news. You're not going to see it on CNN or anything.
Right.
I kind of want to talk about like a few things. There's kind of a lot that's going to be tied into this, but it's going to be viewed through the lens of Big G. And the things I kind of want to talk about are kind of the practice of science, what is like measurement a little bit, and this concept of it's a teaching concept that my girlfriend Dana has taught me called low bar, high ceiling. And I'm going to kind of try to wrap all this together in some coherent fashion a little bit. So the thing I want to talk about is kind of the controversy, quote unquote, behind Big G. So are you aware of any controversy around Big G?
No. I can't. What does it mean to have a controversy around Big G? But let's hear it.
Yeah, it's not really. I wouldn't call it a controversy, but it is.
Before we get into controversies about it, what is it?
Yeah. So this is. What is Big G in the first place?
Yes.
Yeah. All right, that's a good thing.
Just so we're all on the same page.
Yeah. So it's we call it Newton's gravitational constant, but Newton actually didn't create Big G. It just has a historical background, because apparently in his time equations weren't written how we write them now. They were all like ratios, so you didn't really have to worry about Big G, because it was just it's a constant of proportionality. So like they didn't care.
Yeah.
So he didn't actually come up with it. I forget who actually did coin it. I think there's been a couple people throughout history before it was solidified as Big G. But basically, we know Newton's law of gravity, right? It says that in words that any two objects are attracted to each other, proportional to some constant and proportional to their mass over their distance between the two objects squared. And mathematically, I guess we're used to saying that as Big G is the proportionality constant times m1 times m2, the two masses divided by r squared.
Got it. So like Earth is m1 and the moon's mass is m2, and then divide that by the distance between them squared. That's a number, but it's not a force yet until you bring in that constant G.
Yeah.
That turns those numbers into, which are kilogram times kilogram divided by meters squared. That's not a unit of force. So to get it into units of force, we scale it by this factor of G. So we can compare the strength of gravity to the strength of like a spring or something like that. And they're both the correct units of force, which are newtons.
Yeah. And the thing about G is it's very small. It's a pretty small constant. Maybe not the smallest constant, but quite small.
What is it? Let's do just SI units.
Yeah, so roughly it's 6.67 times 10 to the negative 11. What would it be? I'm not sure the exact units off the top of my head.
Yeah.
Whatever you need to multiply to get kilograms squared over meters squared to be. So it's like what, like meters cubed, I think.
Yeah, meters cubed divided by kilograms seconds squared. I'm looking, I just quickly looked it up. I don't know that off the top of my head.
Oh, you know what? I'm looking at, there's literally a chart in front of me that tells me, meters cubed divided by kilograms divided by seconds squared. Yeah.
Yeah. So yeah, something, it's 6.67 times 10 to the minus 11 in SI units to get the units right. A tiny number.
Yeah. And so the reason I stopped, I just said 6.67. Mm-hmm. This is kind of the root of the controversy is I'm going to post a little thing in Slack for you to look at. G is actually our least known universal constant. I guess one thing I should say is G is a universal constant, or we think it is, right? It's one of these numbers like mass of an electron or Avogadro's number, magnetic constant, the G factor you were talking about earlier. It's like one of the fine structure constant. It's one of these like constants of the universe. Mm-hmm. And it's actually the first one, I believe, that we've ever measured. It was the very first one. And we did that in 1798. We'll talk more about that in a minute. Yet it is the one that we still know the least precisely. The first one we measured, we barely know it. So I just sent Derek a picture on Slack from a paper. We can share it in the show notes. But basically, it's a list of quantities, constants, and it has all of their uncertainties listed. So like the speed of light, that's an exact number because the way we have defined our units. Magnetic constant, exact number.
So yeah, it's the relative uncertainties is like the uncertainty divided by the actual number. So like, yeah, some of those, there is no uncertainty because we've defined those constants to be what they are. So uncertainty is 0. And then other ones we're like, Planck's constant, we know out to a certain number, and then it's not, then it's uncertain after that. So like, what's the ratio of the uncertainty to the number itself?
Yeah, exactly. And so that's what this table is looking at. And if you look at it, so you kind of think of it when you look at this stuff up a lot, they kind of talk about it in sort of a percentage, except it's much smaller than a percentage, which is, over 100. So they typically talk about things in parts per million or parts per billion, which would be instead of dividing by 100, you divide by a million or a billion. But that being said, the Rydberg constant is a factor of 10 to the negative 12. So we know it very, very precisely. That's like 5 in 1 trillion, right? And if you go down this table, you'll see it's like to the minus 10, to the minus 10, to the minus 8, to the minus 7. And then you get to the Newtonian constant of gravitation. And you see in 2010, it was minus 4. And in 2014, it was minus 5. I think it's still minus 5 now. In 2018 was the last time they updated it.
Yeah. So they're improving on like experimental results to get that uncertainty lower and lower. And so, it's like right now, well, if it's 10 to the minus 5, that's 1 part in 10,000-ish, right?
Yeah.
Yeah. So that's bad in terms of physical constants. We want to know them to more than 1 part in 10,000 if we're basing like physical theories on it. Like how strong is gravity? We don't know to 1 part in 10,000. That's not great.
Yeah.
And I think these are a little outdated. Like you said, it ended at 2014. And I just said the H1, Planck's constant. And I think we've now fixed Planck's constant, just like we used to have. Yeah, like the top ones that are exact. I think some of the other ones are now exact.
Yeah.
So the redefinition of units.
This paper that I'm going through was written in I think it came out. Let me just check. It came out in July 2020, but it's kind of referencing things pre 2018.
Yeah.
So
in 2019, we redefined a whole bunch of stuff.
Yes,
like Planck's constant. So anyway, yes, just wanted to highlight that point.
Yeah, but the concepts are still there.
Right. And gravity, the Newtonian one down at the bottom of the list is not great.
Yeah. And so that's slightly the controversy is it's not just that we don't know it very well. It's that we have values of it. Many people have measured it, and we have values of it that disagree. So we have values not that just disagree, but that are mutually exclusive. And we'll talk about more about what that means in a minute. But I kind of want to get to how I kind of stumbled upon this, because there's a slightly interesting paper that I read as well that will kind of lead us into how G is measured a little bit, and then we'll kind of come back to the controversy. So this all started for me from a paper that was in Nature that came out of the University of Vienna from, Tobias Westphal, Hans Hapach, Jeremias Pfaff. I'm very sorry for mispronouncing all of your names. Marcus Aspelmeyer were the 4 authors. And what they managed to do is they measured, they were able to detect a gravitational attraction between 2 90 milligram BBs. And that out of context, maybe that sounds like nothing. Like, okay, why is that interesting? And so to kind of put it in perspective, the forces that they were measuring, like the expected force between 2 90 milligram BBs, they're about 2.5 millimeters apart. What is about 9 times 10 to the minus 14 newtons. So, tiny force. Mm-hmm. To give you, a comparison, I think I want to start doing more comparisons to real life. The weight of a red blood cell, the mass of a red blood cell is about 27 picograms, according to a quick Google search. So, take that semi with a grain of salt. But the force, if you were to put that on a scale and measure its weight in newtons, is 2.7 times 10 to the minus 13. So they're detecting a force that is less than the force between a blood cell and the Earth.
Right.
Another way to think about this that I thought was interesting too is, we're still in a pandemic slightly, hopefully coming to the end of it. But we've all had to stand 6 feet or 2 meters apart from each other. Mm-hmm. So the force between 2 average 62 kilogram human beings, which is, I guess, the world average mass for a human being, standing 2 meters apart, is 6.4 times 10 to the minus 8 newtons. So
quite a bit more.
Yeah. So you feel that force just standing, you don't register that force, but it's present.
There.
Yeah. So that's how small this is. It's 6 orders of magnitudes, 1 million times smaller than the force you feel standing next to your friend 2 meters apart. Mm-hmm. So it's just incredibly small force. It was kind of I was a little amazed at the fact that they were able to do this. Mm-hmm. And the way that they did it is they kind of did a modified Cavendish experiment. So to explain that a little bit, as I said, well, I guess let me try and rope you in a little bit. Do you remember Cavendish and his experiment?
I do. Yeah. There used to be an example of it in our physics lab, one of the setups. I think students used to do that in that lab class at Santa Rosa Junior College. Not anymore. But yeah, they had a demo and setup. I think I did it actually at some point in my physics career.
Do you want to explain it?
Yeah. From what I remember, it's you hang from a very fine thread or fishing line, very massive objects kind of on a balance, kind of imagine a dumbbell, like an old cartoon dumbbell.
Yeah.
Two massive spheres on either end of it, right? Yeah. And it's hung balanced by this thread in the middle. And then that dumbbell is free to rotate around the thread that's holding it up. And the way to get it to rotate is to put other masses on either side of the dumbbell. As imagine they were magnets instead of gravity, put magnets in place that would get that thing to rotate around the thread. But they're not magnets. They're literally only just massive objects. And the gravitational attraction would cause the dumbbell to twist. And the thread itself would allow it to twist a little bit. And you measure how much it twists and you work out the physics required to get that twisting to happen. And from what I remember, you set up a laser at some point with a mirror in the middle of the thread. And the laser is projected very far away because the amount of twisting is tiny, but you can amplify it by having a laser reflected on a back wall of a room that's 100 feet away or something. And then if that laser position on the wall moved, 2 feet, then you can work out the triangle and see how much it actually rotated around the thread, and work out the torsion of the thread, I think, work out the force, and figure out how strong gravity has to be.
Yeah.
That's what I remember about it.
Yeah. So that's pretty much it. Just a slightly different way, maybe I want to see because it's hard to imagine. So I want to see if I can get the viewers to imagine a little bit. Is like if you were to imagine sticking your fists straight out 90 degrees to your torso, and just holding them out. Where your two fists are would be the two masses hanging from the thread, and you bring masses close to your fists, one in front of you and one behind you on opposite fists. So like your right fist would have a little mass in front of it, or a mass in front of it, and your left fist would have a mass behind it. And then the gravitational traction will cause you to rotate. So your right fist and your left fist both go towards the mass. So you turn your body when you do that. And then if you imagined a mirror on your chest and you shine a laser at that mirror and bounce it off, that's the mirror that you were talking about. And then you can see where it hits the wall. Will tell you kind of where your chest is facing.
Yeah. And it's such a tiny amount of twisting that, I remember setting it up, and I think we had to wait a week for it to settle, and then we could do the experiment. It's it was like everyone on our floor in that physics building knew that the Cavendish experiment was happening that week, and we're not supposed to slam doors because any stomping of feet or closing of doors too hard would twist the wire a little bit and mess up the whole experiment. Very sensitive.
Yeah. So, Cavendish didn't have lasers and stuff, and he actually didn't design the experiment. He performed the experiment, but someone else designed it, but died before they were able to do it. So Cavendish only did the measurement part of it, but he did this in 1798. So no lasers or anything, but got a fairly decent value. I don't have it off the top of my head here, but I think it was 6.7 or 6.6 something times 10 to the minus 11. But I should say also, Cavendish didn't actually measure G either. He measured the density of the Earth was his goal, and then from that you can actually back out what G would be. So we did that later.
Okay.
But so you can figure out what his G value would have been given the numbers that he did measure. And it wasn't too far off from what we know it to be today. So this group pretty much used the same apparatus. In fact, not all, but many of the measurements since 1798 have basically used this torsion balance to do it. And the reason this is so good, right, is it takes the Earth out of the equation. The Earth isn't pulling on anything. It's only the horizontal forces. You get rid of the vertical forces. So that's why it's a good design. It's clever. So what this group did is it's kind of great. I love it. We had to modernize it. So this is I think this is what I wanted to talk about a little bit with this concept of low bar, high ceiling. And it's a teaching concept that basically says that if you a good question, I guess, or a good activity for students to do, to engage in, is one where anyone can enter the engagement of it. It's not hard to understand conceptually what's happening, but you can go as high with it as you want. So it has a very low bar to entry, but it goes, high ceiling means it just keeps going up and up. You can get more and more and more and more complex. And just like you said, you had people doing the Cavendish experiment. We have it at UCSB. But the ones that we do is it's much closer to what Cavendish did than what people are doing now. It kind of blows my mind how such a simple concept this is, but how detailed they've had to get to try and measure this number more accurately. So what this group did is, so they build the Cavendish apparatus. There's a whole subfield study, not subfield, that's probably not the word. This is like a subgroup of people who study just the wire that you're hanging from. You said like a fishing line or a thread.
Mm-hmm.
Well, there's people that have studied all the material properties of this thread to get the maximum, like you want a good Q factor in making this measurement. And like the higher your Q, the more precise your measurement can be. So there's been people trying to figure out the best way to do it.
Q is like the spring constant of the thread. Is that what you mean by Q? Or
no,
is
it's
it like
a quality factor
Okay.
for the harmonic oscillator type of thing?
Like a resonance thing, like how sharp the resonance peak is?
Yeah. I think it's roughly that. And I think it's related slightly to the spring constant, but also like the physical dimensions of it and that sort of thing. So they've studied how that works. So obviously I think one of the first things you might do is put it in a vacuum chamber, right? So you don't have air hitting anything. But so those two things will help already. But the reason G is so hard to measure, no matter what you do, is twofold. One is its gravity is the weakest force by a long shot, like severely weaker than the electromagnetic force. And I guess I don't think the strong and weak forces really come into play. But its relative strength to the electromagnetic force is it's like almost negligible.
Mm-hmm.
So that means if you have any like small amount of charge just sitting around somewhere on your apparatus, it's going to throw off your results. So like to mitigate this, they do things like this group uses a ionized nitrogen to remove excess charge. I don't know that exact process, but one thing I think that's kind of unique here is this technique that they use was actually developed for the interferometers for gravitational wave detectors.
So that's funny you say that. I was like, isn't there a way to use the new like LIGO stuff to figure out G better? But I guess they're kind of related already through that.
Yeah,
but not
there
quite
might
directly.
Be.
Yeah.
But so they're already related. I just think that's awesome that like we had to do this huge project with this incredible, and I think that's why we need to fund these huge projects, is because we get little bits of science and knowledge and stuff from doing these things that we can apply to other things like just measuring G. And so they do that ionized nitrogen to like remove as much charge as possible. They put a little Faraday shield between the test mass and the source mass, or what the two masses are called. And to isolate it from electrical fields. So you might think, okay, cool, that seems like everything, right? Okay, well, no, you still have to worry about like magnetic fields, right? So you want to make sure the materials that you're using aren't magnetic, that they have no permanent magnets to them, that they're not going to respond to the Earth's magnetic field, that the magnetic field won't magnetize, the Earth's magnetic field won't magnetize anything over time. So they take into account all of those things, trying to figure out, okay, how can we minimize that? Make sure we use materials like titanium and gold that don't really have a permanent magnet. Then it gets even crazier. Okay, so it's like, okay, we got rid of all that. Now it's at the point where like they actually have to care about like the purity and the structure of the mass itself. Like NIST measured this in I forget what year, like early 2000s, and a group in France measured it, BIPM, which is kind of like the NIST of Europe, I think, or at least of France. And they BIPM measured it. They said, okay, we're going to do it, and we're going to send it to NIST, and they're going to do it, and we're going to compare, see what we get. And one of the apparatus that they had to send was this giant granite slab that had, to reduce vibrations, I think, a little bit. And then this very fine, like contact distance measuring device where basically it would move like you can imagine maybe like a needle or something until it came into contact with a surface, and then it knew, okay, I know the location of that surface now, and then it would touch another point of it and another point and another point, so they could kind of map out a surface. They did that because they need to know exactly how spherical is this mass.
Yeah, right.
Yeah,
because there could be like a protrusion or something that causes some. It's not spherical. You can't treat it like a nice point charge, or maybe there's like I'm also imagining they need to take into account like tidal forces because it's not a point charge. Like there is some spatial dimensions to it.
Yeah.
I don't know if there's like that type of gravity also going on. Probably a little bit.
Yeah. I think that is one of the things they have to take into account. They also like have to go through and finally measure the mass of everything, which includes like the glue that they had to use to stick parts together. Mm-hmm. So, they're taking into account so many things and being like so precise. And at the end of it, you're still not like, you could do all of that as best as possible. But one thing you can't do is shield gravity, mm-hmm. right? We don't have a way to do that. I'm looking forward to the day when we do. But so for instance, like I just said, the force between two people standing 2 meters apart is 1,000,000 times stronger than the force that they were trying to measure.
Right.
So having a person in the room would affect their like someone standing 2.5 meters away was roughly the same amount of force on their test mass as the ball, the other mm-hmm. the source mass was. So that no one could be in the room. Mm-hmm. They also had to worry about a tram that was 50 meters away.
Yeah,
that would cause enough force to make things happen, and or just people walking around with vibrations and stuff. So like to eliminate all this, they measured it over winter break, mm-hmm. and they did all their runs between like midnight and 5 a.m. Mm-hmm. to like counter all these things. So they do all of this, and then just to let you know, the way that their measurement works is it isn't. They still use the laser in the mirror, but they did this process. I think it's called heterodyning, but I'm not 100%. But what they did is they actually took their source mass, which is the one not hanging, and they moved it back and forth at a frequency that was much larger than the resonant frequency of the pendulum, the torsion pendulum. And that would cause the torsion pendulum to slightly oscillate at a particular frequency. And then they did kind of this convolution Fourier transform thing on the time series to get like a force spectrum. So basically like, a power spectrum, but with force instead. And they could see a spike at the frequency in which they were driving it at was the response of the torsion pendulum.
Oh, you just reminded me. Yeah, I think I described it a little bit wrong where I said, in my head, I was imagining it deflects and then you go look at how far it deflects. And in my head, it was like, oh, the laser is just stationary at that deflected point. But you're right. It's a harmonic oscillator. It oscillates back and forth around the point before you added the masses that caused the torsion. I forgot that. So yeah, that makes sense. Then I get the Q factor now. And yeah, the torsion is like a harmonic oscillator spring, but it's just a wired twisting. Like you've probably done it where you like wound up a pencil in a, shoelace or something like that. Let it go. It would just like unwind and then kind of wind back up the other direction, oscillates back and forth.
Yeah. But no, you weren't incorrect in your first, what you said in the first place either. And you weren't incorrect with what you just said. There's actually like quite a few ways to use this apparatus to measure G in the first place. One is by waiting for it to come to a steady state where it's only pointing roughly at one spot on the wall after it's come to equilibrium. But it's not as accurate to do it that way. What they tend to do is measure its acceleration. And from the acceleration, they can pull out G.
Got it. Okay.
This group, I just told you kind of every detail that they took into account, everything that they did. They were able to detect this force between two 90 milligram gold BBs, which is astounding. And then they measured G. And what did they get for G? I don't remember the exact value, but it was 9% different than what we say the accepted value of G is.
Oh, like just completely shifted, not like the uncertainty's off, but like the number itself is different.
Yeah.
Okay.
The number itself is just different. And so that whole thing is what got me down this little rabbit hole of like, wait, why is it, seems like they did a real good job. Why is it so different? And they kind of talk about it in the paper. They say, there's all of these factors that can be contributing to systematic error in our measurement, or systematic uncertainties in our measurement. And we don't have a way of accounting for them. These are just guesses. So we can't really say, we couldn't factor those in mathematically and then recalculate, gee, this is just what we measured and we think it's wrong because of this. But so that led me to be like, wow, they're so far off. Like, I think the one that we have at UCSB, students often get better than that. I mean, it's much larger masses that they're dealing with. So the forces are a lot bigger, but so that kind of surprised me. And so I started looking into like, oh, well, what is G? How do we know what it is? And that led me to the quote unquote controversy behind it. And
so
go ahead.
Are they right?
Well, it's unknown is the answer. Probably not. Is would be what I would say. But the controversy is here. Okay, all right. So now I'm going to give you another plot. I just sent you two new pictures. They're both from this paper that talks about the measurement of G that was led by Chao Zhu et al. And they measured G themselves, two different methods, and then also kind of talk about the history of it all in this paper of it. But so the two things I want to point out is that first plot I sent you it's a plot of a lot of the main measurements of big G since 2000. And you'll notice that what is the accepted value right now? They don't actually show it on this plot, so I'd have to look it up. Because it actually matters.
6.674.
Okay,
that's what I'm seeing.
674. So you can see that's a nice point on this plot, or it's labeled there, and you can see that the plot has a lot of points which indicate the average measurement that they made, because they made a bunch of measurements of this. And then there's error bars on all the measurements. And that's with what the window is that they say in which they think the measurement is. So maybe I kind of want to talk a little bit about that more. Maybe if you want to chime in there. But the thing to highlight in this plot is, okay, co-data, which is like kind of the best data we have for all of the fundamental constants, says it's 6.674 times 10 to the minus 11. None of those really fall on that line.
Yeah.
And some of them even fall outside of that line with an error window that doesn't ever even cross that.
Yeah. The CODATA recommended value is 6.67430. And the 30 is uncertain up to plus or minus 15. If that makes sense. So 6.67415 up to 6.67445, I think is what you could say. So 6743. Yeah, they all seem in that plot, they kind of hover around that. That's definitely where most of them are.
Yeah.
Is just above 6.674.
But you can see though that they're also, there's a few that are at like 6.672.
Yeah, no, totally.
There's some at 6.6758, maybe 6 there. And then the other thing is that even the ones that are close, their error bars don't overlap.
Not necessarily. Yeah, there's a few that don't.
So this is the controversy, is that we have measured G so many times, and we've said we think we know G to this precision, but it's impossible for all of these people to be right.
Right.
And so, okay, maybe we'll loop back slightly here in a sec. But the other small table to look at is this is all of the other image I sent is all of the co-data values.
Different years.
For G over the years. And the interesting thing to look at for me is just the relative uncertainty on the right in parts per million. So you notice it kind of goes up and down quite a bit. Right.
Yeah. So in the 70s, it was 600 parts per million was the uncertainty. And then it went down to 128 parts per million. And then in 1998, it skyrocketed to 1,500 parts per million. But then it went back down to 150, 100, 120, and now it's 47 parts per million.
Yeah, I think the 1998 one is because they kind of had a bit of a crisis where they had a few people make measurements that were just drastically different. So co-data kind of looks at a lot of people's measurements and tries to parse together like how to weight them to be, okay, what is the right actual value? And I think they had some that were quite different around 1998. And they ended up realizing some of those were a mistake. And that's kind of why it skyrocketed and went up. But like they change it a lot is my point, is because they don't know because of this reason that people make these measurements and they don't agree and they don't even overlap.
Right. I just sent you an image of the same thing, I think, plotted as a function of time.
Yeah.
Those are the recommended values of G since 1900 with their uncertainties. And yeah, some of them don't overlap. Their uncertainties are off from other years' data.
Especially the later ones, like the post 2000 ones too. Like the ones pre 2000
uncertainties, but they're different from each other.
Yeah.
So what's G? It changes every year.
Yeah, pretty much every 4 years.
We solved it. We just need to measure every year and we get a new value. We now have a time-dependent function of G.
Yeah. Well, and I think the other thing to highlight here is I described one method that this group at Vienna did to measure G. A lot of people still use the torsion pendulum, usually not with BBs, usually heavier things than that. I don't think that the Vienna's goal was to measure G. I think they were just trying to measure the smallest gravitational force, or detect a tiny gravitational force. But there's all these other methods that people have done to kind of summarize a couple of them. One is a simple pendulum. So you just hang a bob, right? And you bring another mass next to it. And that's going to cause some small deflection of the pendulum towards the mass that you brought close to it. And so if you can measure the gap between the two, you can then figure out what G is. And this is done using Fabry-Perot interferometers. So they put two mirrors, one on the test mass, one on the source mass, shine a laser or a microwave in between the two, and measure. That allows you to very precisely measure the gap between the two objects. One that I liked a lot is cold atom interferometry. So basically, you trap a bunch of atoms that are very, very cold, so they all kind of have the same quantum state. And you kick them with some light, and that causes them to move upwards or stay stationary. And the ones that move upwards there's a mass above them, so they kind of get maybe pulled by that mass a little bit. And then you kick them again, and they all recombine. And you measure some quantum state again, and that's a very rough overview of 10-second overview of atom interferometry. So don't quote any of that. But from all that information, though, they can also measure G based on kind of the arc of the cloud of atoms as it went up and came back down when it got near a mass, a test mass. So, I said quantum and atom interferometry. And so it all sounds like, precise, like this, high tech at least. It's actually one of the least precise methods right now, but very different. If you see it's lens 14 is what it's labeled as on that. one that
in the
I
chart.
sent. Yeah. And you have,
super low and big error bars. It's the lowest. It's the lowest number for G, but it also has very large error bars. But they're still, the accepted value is outside of those error bars.
Yeah. So and there's this beam balance, which I don't quite. It's basically kind of like a Watt balance, which is what we use to define Planck's constant now, I believe. But it's a very fine balance. That's another method. So we've tried measuring G with a bunch of different methods, and we've said we know it to this precision, but then a lot of these just don't agree with each other. So we have a lot of systematic error somewhere in these measurements. We just don't know really what G is. That's kind of the whole thing, is what we don't know. And the nice part, the kind of the thing one of the things I want to talk about is like, this is such an interesting and easy to understand from a high level, like, process of science,
Mm-hmm.
like this is people measuring a constant, and we don't know what it is, and we're all trying to decide what it is. Like I'm thinking back to like teaching, when you like a lot of times you measure little g, 9.81 meters per second squared, and when you do that in a classroom, a lot of the time students will say, "Is this right? Did I do it right? Is this the right value?" Like, they have a thing that they want to compare against, and you don't find that too often in the lab, in at least the educational side of things, that isn't the case, that there is not something you can compare your answer to that is accepted and known better than you can do it yourself. And not that in a educational environment, students can measure G better than how these people have, but it's truly like a actual process of science, where if someone says, "What is G?" the right answer is like, we don't have a great idea. We have a rough idea. And you can actually like see the process of people making measurements and arguing about which method is better and what is more true or not true. And it's not something like the fine structure constant, or the G factor or whatever, the mass of an electron. It's such a like tangible, at least to me, it is like a tangible thing.
Right. How strong is gravity? It's like pretty straightforward.
Yeah. So I just think it's an incredibly like cool small subfield of science is hey, we don't know what this value is, and we're still trying to figure it out, and it's active and it's live, and you can watch people try to do it.
Right. Yeah. And I think to the education point, we teach in class, we teach in like lab to compare to the accepted value, but we don't know what that value is. Like, there are accepted values, but as we've seen, it changes over time. Different years, you have different accepted values. And yeah, some of these experiments, like the cold atom interferometry, like their number's not right. And like you would say, it's wrong, but they're just honest. They're like, yeah, we did this experiment. Here's what we got, Don't know what it means. Could be interesting, could be not interesting, but here's what we did. Here's how we did it. And here's the value we got. We're publishing. And so it's not like in a lab class in college where you get a number and it's off and you're like, well, I did something wrong. Let me go back and fix things. Like, maybe, but if you understand it well enough, as these people do, they're confident in saying, in this experiment, this is what we got. Who knows? Maybe they found new physics and it's worth just reporting what they got and how they got it. I think that's valuable.
Yeah, exactly. And it's really a good example of how science should be done, right? You don't want to actually go back and say, oh, we didn't get the value of G that CoData says we should get for G. Like, let's
not publish.
Or let's tweak till we get there.
There's also the people who, They were honest, but it's always the thing to point at and make fun of is the people who got the faster than light neutrinos. And everyone's like, there's no way those neutrinos are going faster than light. And they were honest. They said, we agree. We don't know what's up. Here's our information, though. So here's how we did it. Here's what we got when we did this.
Yeah.
And they were wrong, but at least they were honest about it. They're like, we understand. We're not trying to shake up faster than light physics being possible. We got a weird number in this experiment. Somebody find what we did wrong. And then they found it. So. But yeah, there's always those situations where it's like, we understand this is not matching what we theoretically expect to happen. Yeah, but I guess that's a little bit different because if neutrinos go faster than light, that opens up a huge new realm of physics. Whereas your value for a gravitational constant being off by, a few percent is fine. Physics doesn't break necessarily.
Yeah, well, it does have some implications potentially. One small side note I wanted to talk about with that exact statement that you said is while I was, kind of Googling and looking up YouTube videos and stuff, talking about this, I stumbled upon this religious video. I didn't realize it was religious till I got part of the way into it.
I snuck it in there.
I had to see where it went. And this guy, I don't know what his religious status was, whether he was like a minister or priest or just some guy proselytizing, but he claimed like, okay, God is real because if G, this G we've been talking about, was off by like it was like 40 parts in like a billion or something, or like a trillion, like some. No. It was worse than that. He said if it was different by 1/10⁴, then it's impossible for
God exists.
It's impossible. He said if it's different by 1/10⁴, then it's impossible for the world to exist, the universe to exist as we know it now. He's basically saying if it was different in either direction, if it was 1/10⁴ bigger or smaller, the universe couldn't exist. Therefore, the random chance of that happening proves God exists because there's no way that could randomly happen. And the thing that I love is like, if you listen to this, everything we just said, you should easily be able to refute that because we don't know the value of G to more than 10 to the 5, 10 to the minus 5, Like there's no way you could make that claim because we don't even know what it is.
Right.
We don't know any, except for the exact ones. We don't know any constant out that far.
Well, we define them to be that. Yeah.
Yeah.
I think, that falls under the bigger principle of the anthropic principle of like the only reason we're here to even ask what the numbers are for these values is because they are the numbers that make it possible for humans to exist. And for observers like us to ask those questions. Therefore, they must be those numbers. But you don't need religion for that part. There's cosmologists making those arguments and thinking about things in that way. And there's arguments against them too. But I loved how you have to be that precise.
How well his argument fit into exactly what I was trying to talk about. It's there's no way that could be true because we just don't know it.
There's the not religious, but the counterexample of good science. So I guess an example of bad science, which is basically confirmation bias. Like if people only published data where the value for G was close to the accepted value, then we would see that like clearly is not correct. We would see that representative in the data and that it would slowly over time approach the correct value. And there's an example of that with I think it's the charge to mass ratio of an electron, which was the Millikan oil drop experiment.
Yep. There's a lot of controversy there.
Yeah. It's kind of the same thing, but in reverse, in that Millikan was this world-renowned physicist who did the experiment and figured out what the charge to mass ratio of an electron is and published it. And then if you look at his number, it's not right. Like compared to what we now know it to be, his number that he published was wrong. And people, I think if you plot the accepted value for that ratio over time, it has a trend approaching what we now know it to be. And it starts at Millikan's value. And so over time, people didn't want to contradict Millikan, but they were okay with like a little bit of contradiction. Like they'll inch higher than his value and approach the correct one. But if they did an experiment that was like, maybe it was actually what we now know to be correct, they didn't publish it for fear of contradicting the great Millikan. I don't know how true that is, but it's usually used as evidence of confirmation bias in science, and that people don't want to, contradict what's quote unquote known too much.
Which is why it's so important that people are publishing all of these
things
values that
wrong,
disagree.
But not really wrong, quote unquote wrong.
Yeah. Because who knows? Maybe we have some Millikan level confirmation bias with some of these values of G, and that's why they're there, and it's I mean, if you look at the plot that you sent me, you can definitely see there is a little bit of a trend towards a value.
But then it fluctuates though. More modern times it does fluctuate, but it started low and then it's increasing over time. But the error bars were just massive in the early measurements.
Which is also really good. Like and I think one I want to say make one brief statement about error bars, I guess, or better yet, I like to call it uncertainty. I don't like the term error. Shout out to what is from SRJC, the Linda.
Oh, Linda,
yeah. She's the one that turned me off of using the term error. So we'll post these plots, and when you look at them, the error bar typically is rough. It's usually 1 or 2 standard deviations, but I think the standard is, I try not to use the word standard. The standard though is 1 standard deviation. So what they're saying is there's a dot in the center that says, we think this is the best guess at the value, but it could fall. There's a 68% chance that it falls anywhere in this range.
Right.
And there's a 32% chance it falls outside of that range, basically.
Like if you repeated the experiment over and over and over again, 68% of the time it should fall within those bars.
Yeah, exactly. And so when you have two that are two measurements where the center points are very far away from each other and the error bars don't overlap, it's pretty much saying that these two measurements are not compatible with each other. There's almost no chance that they would ever agree on what the real value is.
That's I used to ask my students this when they did the Higgs mass measurement. They released the data and said, here's the 2 experiments that measured the mass of the Higgs particle. They released them with the uncertainties. And so I'd ask my students, I'm like, do they agree? They're acting like they agree, but do they? Because the numbers aren't the same and the uncertainties are different. But the error bars, the uncertainty ranges, they do overlap. So that's good. But the centers, the points themselves aren't necessarily in the range from each other's experiment, which is interesting. But they're just like, yep, that's what it is. But is it? 2 people got different numbers, but I guess it's fine. But I know why it's fine. But what a good example currently that's in the news right now in physics is the another G value from the G-2 experiment of muons. And theory comes up with a number in uncertainty, and then experiment comes up with a number in uncertainty, and they do not match, and they fall outside each other's error bars. And they're like, what's going on, guys? So that's the situation where there is new physics, and it is a disagreement. And another example of a G, but lowercase this time. Which maybe we can do a whole episode on that. But it ties in with talking about the published values with their uncertainties and what is and not within the range. And is that new physics, or is it just a weird consequence of the experiment? And it seems like people aren't thinking new physics when they publish a G value that's different. They seem to be leaning towards like, it's just really hard to measure this thing.
Yeah, it is that there is some small potential implication for new physics. I think I've heard it kind of shows up in 2 ways. One is it is theorized that it could be actually changing with time slightly. As that's a potential hypothesis. Not that anyone's like
And
advocating that that's 100% the right answer.
That's not to say like the 1973 experiment is different because it was in the past by like 50 years, but that's not that scale of change with time. It's like over the cosmological time scale. Like we're talking billions of years where there's
but if we could measure it precisely enough, though,
you could see
then we would be able to see it change over 50 years or something if it was precise enough. And then I guess one other potential way that it can factor in is kind of into dark matter and how we explain the rotation of gravities or of galaxies. Sort of thing. I didn't really look into that side of things too much, but I guess it factors into Mond theory, which is modified Newtonian dynamics, which is another explanation for the galaxies spinning at a constant rate.
Yeah, I just jumped down to the bottom of the gravitational constant wiki page for values, and it talks about the new experiment you were talking about, and it says it's a difference of 2.7 sigma between the two results. Basically, their value is different than the accepted value, 2.7 sigma, and so new physics, quote unquote, is usually requires. Do you know what it is? I think it's 5 sigma.
5 sigma.
Yeah. So we're not there yet for new physics, but 2.7. Yeah.
And I think. Wait, sorry. You're talking about little g?
No, excuse me, big G.
Oh, though this one here.
Yeah.
And I think even if you did do that measurement at this point in time, if say it was, 5 sigma difference, it wouldn't necessarily indicate new physics still yet, because this is just such a hard thing to if 10 other people performed, someone else performed your experiment and 10 other people performed different experiments and they all kind of measured it. And they got values closer to that, then maybe we'd be there. But it's just, science is a process. It's a breathing thing. It's a living thing. One other interesting thing here too is that all these different types of experiments that all measure G to be different values with different error bars on them that don't are mutually exclusive is a good indicator too for systematic uncertainty or error in the measurement. So basically that's just saying that there's something unaccounted for that is pushing the value consistently in one direction or the other, whereas the uncertainty bars that we were mentioning earlier is more saying that there's random fluctuations in the measurement that we can't get any more precise than this, and it could go kind of anywhere if you were to make a measurement in this range.
Yep. The small uncertainty means you're very precisely knowing your value, but it's totally possible to be precisely wrong. But you're precise about it, but you're still wrong. That's the being wrong part, the systematic shift of everything just being off. Even though it's small uncertainty, you're wrong. Or just different. The Cavendish experiment, just something jumped out at me when reading about that, where there was, it improved upon other methods. And one of them was the Peruvian method for measuring the force of gravity. I was like, what the hell is that? And why is it just given this title, the Peruvian method? Apparently there was an expedition to Peru and Ecuador in the 1700s where they measured the period of a pendulum and checked it as they rose in altitude, climbing a mountain. And so they measured the change of the period of the pendulum as a function of height, which is the Peruvian method for getting G. I thought that was interesting.
Yeah, that's another method where they at the time they didn't actually measure G. They measured the density of the Earth. They were very concerned with the density of the Earth in the 1700s, early 1800s, apparently.
Yeah.
And so you can back out what G is from that measurement. But so I just kind of wanted to highlight this controversy, put it on people's radar, and let them, be able to watch science in action over the next, 20 years.
And if you're going through college and taking a lab class where you do the Cavendish experiment, or you do any experiment to find G, I think we did not Cavendish, but just other experiments to calculate G. and you're asked like, oh, compare it to the expected value. And you're like, no, that's not known. Take your pick. I got lots of them. So maybe I'm right. Maybe it's 8 point something times 10 to the minus 11. Who knows? It's probably not that.
No, I don't think it is. But I really want to use this as an example for our students to really highlight that, when the thing that we're trying to teach you as a physicist is not to measure G really to the right number. It's that we want you to make a measurement and be able to justify the value of that measurement, or not justify it, say this is why it's wrong, but whatever you've measured, be able to explain why it is what it is.
Right. Yeah, I remember telling you a story of something I read a long time ago where some people were doing experiments where they had their, GUI, the graphical user interface of whatever thing they were building, the experiment that they were running, and they covered up on the screen where the actual number that they were measuring is. So basically what the dot is in the middle of your uncertainty, they covered it up because they wanted to set up the entire experiment, minimizing all the uncertainty without being biased by saying, well, let's get this number closer to what we know it should be. Maybe they're measuring the charge of an electron or something. So they covered it up and they just kept doing the experiment, checking every other possible number without knowing what the result of their experiment was, because the other things they were checking was the uncertainties. And so they're trying to get that as low as possible without being pushed to making changes in the experiment to get the number closer to what they know it should be. And then at the end, once they got the uncertainty as low as possible, they're like, okay, we're very confident in this experiment. Then they removed the cover and they got to see what their answer was. And it was pretty close. So yeah, I think that's a good way to think about science, is just get the uncertainty, know what you're doing and how to represent your data. And then at the end, the answer comes out. You can be confident in that answer.
Yeah. And if your answer disagrees with other people, then you have to decide, did we make a mistake or did other people make a mistake?
Right.
And how can we check and see and figure that out? And that's really that's the hard part of science.
Yeah. Yeah. And that's what this, the G-2 thing that's going on. They knew there was a discrepancy, and then they did a different experiment, and they're like, okay, so let's see what it comes out to be. And they're like, oh no, it's still agreeing with the thing we thought was wrong.
Yeah.
So yeah, they're like, I guess theory is wrong because our experiments are pretty consistent. So we got some new physics to explore because things are outside of the expected theoretical values. Well, cool. I wonder if they're going to do some gravitational wave thing and pull out G that way. I don't know why. It just feels correct to do that experiment, but I don't know what it is.
Yeah, I don't know much.
Yeah, those gravitational waves are just too big. I don't know, too small. I don't know what the problem would be, but yeah.
I think what might be the next kind of way people start doing this. Well, I think there's going to be more of the atom interferometry method going on, because it's not terribly hard. I don't think once you have an atom interferometer, it's not hard to set up this measurement if you wanted. But I think one route that some experiments are going to start going in is actually measuring G in space.
That makes sense,
because we're able to kind of send people to space a little more easily now, thanks to like SpaceX and Blue Origin and Virgin and stuff. And I know that there's been some proposed experiments that need to be done in space. So that might be kind of the next way. And and I guess one small thing to mention of why do we care like what the value of G is? I think it was Planck who proposed this, but you can actually define all of your units, like I think length, time, and mass, using the fundamental constants. But I think it's to get time, I think you need G. And you can't actually have this kind of, he was trying to set up this very fundamental units method that you just can't do unless you know G, basically. Was one reason why it could be a useful thing to know.
I like the kind of end of the Wikipedia page. It just reminds me of grading lab reports. Suggested relation with other constants. And this is, there is a good approximate theory of everything relation between the gravitational constant and Planck's constant. And then the Wikipedia editors come in and say, by whom? Year needed. Like, what's your source? Like, who's saying this?
Yeah.
Yeah. It reminds me of grading. Like, you can't just make a big claim and not cite anything. Like, who's saying that? That whole structure, or that whole section in that Wikipedia page is interesting. It's like, citation needed, citation needed, citation needed. Just these wild claims of how G connects to things. Yep. So have fun measuring big G and add it to the pile of our universal constants. I like this. We've gone through this kind of rhythm of you come up with the topic and we record it, and I don't know what it is. I just show up, and then I'll come up with the topic and record it, and you don't know what it is. You just show up. Yeah, it's kind of like today was a Zak day. So thanks for bringing us the gravitational constant, Zak.
Yeah, I think it's works out well because it gives the other person, like, you get to be the question asker,
right?
Type of thing to engage in it, and then. Or in this case, you were the question asker. In the other case, I'm the question asker. And then we also kind of have someone who has a broad idea of how everything's going to go.
Right. Yeah. It's a good pattern. And yeah, if you all have any suggestions for topics that you'd like us to cover, hit us up in Reddit at r/thehyperfine or Instagram at thehyperfine on Instagram. Yeah,
please. I think one way that we could, if you like this podcast and you want more content, I think one great way to help us outside of, subscribing and all that is to actually post ideas to that, because it's really hard for people so really engrossed in physics to figure out what is interesting in physics.
Yeah. Yeah. Everyone jumped on the mu experiments, and I was like, yeah, that's cool. I don't know, not my thing, but I could see how some people would like it, and some people love it. It's like, get so excited about it.
Yeah. Or, but we got one suggestion for, just explaining how a refrigerator works.
Oh yeah. Perfect. Exactly.
And, that is it's a physics topic, and it's interesting, but it's for some eggheads like us, I guess, we're thinking more about G or entropy or whatever. Yeah. And sometimes some of those other questions are just a lot more interesting and down to earth and easy to think, but we just don't think of them. So if you have anything like that, please write it to us.
Right. Yep. Ask Hyperfine. How about that? You can find all this information on thehyperfine.com. It's our general source of all links and all connections. And yeah, you can find and listen to stuff there. Find us on Spotify and Apple Podcasts and everywhere, really, as far as I know.
Yeah. And you can find me on Twitter at Phyzax, which is PHYZAKS. Yep. I have to spell it every time. It's not a good physics handle.
Yeah, not a good Twitter handle to roll off the tongue. I am like tortilla. Yeah, I just went with 2 words. Easy to spell, mostly. So, cool. All right. Well, we will see you all next time. Thanks for listening.